Okay, so really quick introduction to the layout of the periodic table and how it's been built up, how it's designed. Let's get this pen working. There we go. This is what we're looking to cover, the fact that the table's in 4 blocks, S, P, D, and F. This idea of groups and periods, and how those groups and periods are made up, all based around electron arrangements. So this is the periodic table. You can see they're listed in order of increasing atomic number. But rather than just as a long list, they've been broken down into, this is not working, they've been broken down into groups. There's group 1, group 2, 3, 4, 5, 6, 7, 8, all the way to group 18. You've maybe learned to name them 1, 2, 3, 4, 5, 6, 7, 8. But the IB system wants us to bring in the transition metal groups as well. So we're going to use 1 to 18 for the groups. Periods run horizontally, group 1, 2. Very often people, if they look at some periodic tables in their chemistry labs, they'll forget to include hydrogen, helium as a period, so just be careful of that. That's period 1. So periods across the way, groups are down the way. Right. There we go. So how are these things arranged, and what's it got to do with electronic arrangements? Well, in the atomic theory section, we learnt how to do electron configurations. We used a chart like this to build up these lists of how the orbitals are filled up, and we use things like Hund's rule, the Aufbau principle, the Pauli exclusion principle, and we ended up with being able to write these electron configurations. So if we take potassium, which you might just about be able to see is there, it's finishing up 4s1. Right, if we go through this system, it finishes up 4s1, and sure enough, look, it's in the S block, which is this first section, and it's in the 4th period, so its highest energy level is 4, there it is, and it's the first one in the S block, and there's only 2 columns in the S block, 2 groups, because it's S1 and then S2. And then another block that we're going to be dealing with is the P block, which is these 6 over here. So you know you can get 6 electrons in a P sublevel, 3 P orbitals each holding 2, which gives us 6 electrons that can go in there. So if we look at silicon, which is finishing up 3p2, it's in the 3rd period, and it's the second one in the P block, right? So P1, P2 is where it's at. So the highest energy level that's occupied, principal quantum number's 3. There it is in the 3rd energy level. Cobalt, 4s2, 3d7, should be the 7th one along in our D block. So this is our D block. There's 10 groups in there. And if we go along here, there it is, 7th one along. It's still in the 4th period because the highest energy level that's occupied is the 4th one, and it's the 7th one along. You notice we've got this closed shell configuration here as well, just to tidy it up a bit. And the oxide ion, we also learnt how to work these out, but for the purpose of what we're doing here, this isn't very important. Right, so this is useful because not only will it tell us the highest occupied energy level, we can also start to think about valence electrons. And certainly if we look at the old system that we used to use of numbering the groups, if we went 1, 2, 3, 4, 5, 6, 7, 8, we'd be able to say something like, you know, in the outer shell of carbon there are 4 electrons. And when it comes to talking about covalent structures and Lewis diagrams, that's a good quick starting place. Likewise, if we're working out ionic structures and thinking what ions is something likely to make, well, lithium's in group 1, it's got 1 outer electron, it forms an Li plus ion. So we can just have a quick glance at the periodic table to work out what's going on in the outer energy levels, and it will often help us with our bonding section. So this is the table without any names listed in it, and we can give these names to some of the groups. So group 1 is known as the alkali metals, group 2 is the alkaline earths, halogens, group 17, 7 in old money, noble gases, Group 18, transition metals, essentially the D block. We'll maybe see that there's one exception there, which is zinc. When we get onto that, you'll see that it doesn't fit the definition of a transition metal. But by and large, this section here, these are the transition metals. And the F block is made up of the lanthanoids and the actinoids. Generally speaking, on the left-hand side of the periodic table, you've got metals. Right-hand side of the periodic table, you have your non-metals. And in between, these elements are able to show properties of metals and non-metals, and we call them metalloids. So that's what we've covered. That's my list of resources. Thank you.